Hi everyone, I am MD Abrar Fahim. I want to tell you about a really cool kind of a computer today, which is called quantum computer, and a famous algorithm called Shor's algorithm and how to implement it in a quantum computer. Quantum computers are spatial computers that use the magic of tiny particles to solve really hard problems. You know how a regular computer is a kind of like a bunch of light switches? So each switch can be on or off, which we can call bits. So everything your phone or computer does, like games, pictures, videos, is just lots and lots of these ons and offs. But quantum computers are different. They're little switches called qubits. So this is the one of the main difference between the regular computer or the with the quantum computer. So the qubits can be on, off, and both at the same time, whereas the regular computer can only be on or off. So it's like having a magic coin that is spinning in the air. While it spins, it's both heads and tails at the same time. When it lands, only then you can tell it's heads or tails. So because of this, quantum computers can try out many answers at like all at the same time. Instead of one by one like regular computers, like they can use like multiple simultaneous ways to solve the problem. That means they can solve some really hard puzzles much faster. And there is another trick. Sometimes these qubits can be connected in a spatial way, so if you look at one, you instantly know something about the other one, even if they are really far apart or they're really close. It's like having a secret handshake with your friend, even if they're on the other side of the world. Quantum computers use these weird and wonderful tricks to solve big problems in science, medicine, and keeping our information safe in digital world. They're still new, but they could change the world someday. Let's talk about these qubits or tiny switches. So, a regular computer uses bits, as I told before, which are just tiny switches that are either off or on. If you look at a photo on your computer, it's really just a big list of zeros and ones. But a quantum computer uses qubits instead of bits. A qubit can be off, on, or both at the same time. That's called superposition. Remember the magic coin I mentioned before? So while it's spinning, it's not just heads or tails at the same time, right? It's both. But you cannot differentiate its tails or heads. It's both. It's spinning, right? So only when you catch it, like you see that it's heads or tails, right? So that's what a qubit is like before you check it. So now sorry now here's where it gets even cooler. Okay, so if you have two qubits that can be entangled, so entangled means if you look at if you look at one, you instantly know about the other one, even if they're really far apart or they're really close. So Einstein mentioned this situation as spooky action at a distance. So it's like having two magic walkie-talkies that always say the same thing, no matter how far they are. And the more qubits you have, the more powerful your quantum computer gets. With just 20 qubits, you can keep track of more than a million things at once. So, how these qubits are used? Like, how do we actually use these qubits to do our stuff? So regular computers use things called logic gates, logic gates are like little puzzles that flip the switches on to off or off to on. On the other hand, quantum computers use quantum gates. These gates don't just flip the switch, they can spin it, they can mix it or connect it to the other qubits in all sorts of ways. One cool thing is that quantum gates can do things backwards too. Like imagine you are in a maze. A regular computer has to try every path one at a time to find the way out. On the other hand, a quantum computer can try all the possible paths at once. Then it uses a trick called interference to cancel out the wrong paths and find or select only the right ones. Like another example, there is a spatial gate called Hadamard gate. So it puts a qubit into superposition. So it's both 0 and 1 at the same time. Then we use more gates to mix and match with the qubits, and at the end we check them to get our answer. That's why quantum computers can be so fast at solving certain kind of puzzles. So let's dive into another section. Why these quantum computers are is so powerful. So why do we care about these quantum computers? So they're not here to replace your phone or your laptop. Instead, they're really good at solving specifically hard or really hard problems, such as figuring out how molecules work inside of something, which helps scientists make new medicines, or finding the best way to do something like planning the fastest route for a delivery truck, or keeping your information safe, because some codes are hard for regular computers but easy for quantum ones. So quantum computers are like super smart puzzle solvers for the trickiest puzzles ever possible. So now that we have the basic of how quantum computers work and why they're so amazing, let's talk about a famous quantum trick called Shor's algorithm. This is a way quantum computers can break some of the secret codes that keep our information safe on the internet. So, what is Shor's algorithm and why is it a big deal? So, a smart person named Peter Shor came up with it in 1994. It is a special trick that lets quantum computers break big numbers into their spatial building blocks called factors, like super quickly. So, why does this matter? Well, a lot of our online safety, like our parents' banking systems or our private messages on social media, like these all are depends on the fact that breaking big numbers into factors is really hard for regular computers. For example, if I give you two secret numbers like 17 and 23 and ask you to multiply them, you get 391. Easy, right? But if I gave you 391 and ask you to figure out what are the two original numbers are, which were two primes, then you cannot do it. Like then it becomes hard. So for small numbers, you can do it like one or two digits. But for really big numbers, it would take a regular computer longer than the age of the universe. So, but with Shor's algorithm, a quantum computer can do it much faster. That's why people are excited and a little bit worried about quantum computers. So, how Shor's algorithm works? Let's talk about it. So, um, first of all, it picks a random number. So, like pick a number that is not a factor of the big number we want to break. Next, find the pattern with a quantum computer. So this is the magic part. This is the quantum computer does, which helps us to break really big numbers, big factors. The quantum computer uses its qubits to find the hidden pattern called the period in how these numbers repeat. And last step, figure out the factor. So once we know the pattern, we use some regular math or like GCDs to find out the secret building blocks or factors of the big numbers. So the coolest part is the step two, where the quantum computer uses superposition and interference to check lots of possibilities at the same time. So what this program does. Let me show you what I did step by step in Google Colab to run Shor's algorithm to find out the example secret factors of 15. So first, setting up the quantum circuit. So I used some special code in Google Colab from importing from Quiskit to set up my quantum computer. So I used as I said, like Quiskit. So it is like a toolbox for building quantum computers in your home PC. So next, I told the quantum computer to do some spatial math, like some called modular exponentiation. This is where the quantum computer mixes up the qubits in a way that hides the answer as a secret pattern. So it uses a number a equals to 7, for example, and the number we want to factor is equals to n equals to 15. We took 15 here, like small number, so that we can factor it easily. Then I used a quantum trick called quantum Fourier transformation. Like this is like using a magic magnifying glass to spot the hidden pattern inside in the qubits. So it helps us to find the period we would solve the puzzle. Now I created a quantum circuit. I uses 8 counting qubits and 4 more for the math part. I set up my qubits and put them in superposition, ready to try all the answer at once. Yeah. Next, I tell quantum computer to do its special math trick, modular exponentiation. This mixes up the qubits to hide the answer as a secret pattern. Then I use the quantum Fourier transformation, which is QFT, which is the advanced version of natural Fourier transformation. This is like using a magic magnifying glass, as I said, like to find the hidden pattern. This step helps us spot the pattern we need. So next, I measured the counting qubits. Like measuring is like catching all the spinning coins and seeing how they land. And answer pops out as a string of zeros and ones. Okay, here here you can see our output. Yeah. So after that, like since the real quantum computers are really small and noisy, so I have to run it in my computer. So I used a simulator for that, which is called Chasm Simulator in Google Colab. This lets us see what would happen if we had perfect quantum computer. So here is the histogram of our output. So now let's take a look at the results. So here's what I found here. So the most common output here is showing like the binary was like 11000000, which is the decimal value of 192. Like from this, I figured out the regular period was 4. And then once I had the period, I used a little more math to find the secret factors of 15, which is 5 and 3. So my program uses quantum trick to break 15 into its building blocks, like just like Shor's algorithm promises, right? So a quick summary of what my program does here. So I build a quantum circuit in Google Colab using Quiskit. The circuit puts qubits in superposition, does molecular exponentiation, uses quantum Fourier transformation, and measure the result. Then we put the like draw the text and the histogram. So the simulator shows us the most likely outcome as of 15 is like the factors of 15, which is like 3 and 5. This shows how quantum computers can solve special puzzles much faster than regular computers, using the magic of superposition, entanglement, and interference. So right now, the another question. So why we ran it on a quantum computer? So yeah, you might ask why not just use a regular computer for this? It's like 15, it's easy, right? For small numbers like 15, we can use the regular computer or our classical computers. But for really big numbers, regular computers would take forever. Only a quantum computer can do it quickly because it can try so many answers at once. Like also running this on a real quantum computer lets us see all the weird and cool things qubits do, like being random, showing patterns, and acting in a ways like regular computers never could. So what did we learn here? Course algorithm shows how like the quantum computers can solve problems that regular computers just cannot handle, like yeah, just cannot handle, at least not in any reasonable time, I'd say. So we used a special program to show how a quantum computer can break a number into its building blocks using its amazing powers. Like quantum computers are still new and they're not perfect yet, like you cannot directly use it yet, but one day they might help us to solve the huge problems in science, medicine, and keeping our digital world secret safe. Thanks for listening. I hope you understand how what is quantum computer and how it runs and how we implement our the Shor's algorithm here. And I appreciate that you listen. Thank you so much.